Welcome to our deep dive. We're going beyond those fridge magnets, the kind everyone's familiar with.
Right.
And today we're diving deep into magnetism,
Yeah.
a fundamental force of the universe. We're going to be uncovering how magnets interact, and we're even going to explore Earth's magnetic field. We'll even go back in time a little bit and see how ancient rocks reveal our planet's magnetic past. I'm excited.
It's going to be fun. What I think is so fascinating about magnetism is that it's not just a force of attraction or repulsion.
Yeah.
It's actually this dynamic phenomenon that shapes our planet and guides animal migrations
Wow.
and powers a lot of the technology that we use every day.
That's amazing. I think we should start by building our understanding of magnetism from the ground up.
Okay, yeah,
But I think it's fair to say that a lot of our listeners are already pretty familiar with the basics.
I would think so, yeah.
So I think we can skip those elementary school definitions,
Okay.
like what is a magnet,
Right.
and jump into some of the more fascinating details.
Sounds good to me.
Yeah.
I think most people, when they think about magnets, they know about the North and South poles.
Yeah,
And opposites attract.
sure.
But have you ever thought about why that actually happens? It all comes down to the invisible force field around every magnet.
Oh, okay.
It's called a magnetic field.
So it's not just the physical magnet that we can see and touch.
Yeah.
It's this invisible field around it.
Exactly.
That's really doing the heavy lifting here.
You got it.
Yeah.
Imagine these fields as sort of a magnetic aura extending outwards
Okay.
and interacting with other magnetic fields.
They're invisible, though, right?
They are invisible, but you can kind of visualize them, like
Mhm.
almost like lines of force.
Okay.
And these lines, they always form closed loops.
Uh-huh.
And they never cross. And the closer these lines are packed together, the stronger the magnetic force.
So it's almost like a visual map
Yeah,
of the magnetic force,
Right.
where, like, more crowded lines, that means a stronger pull or push,
Yep.
depending on, if it's north-south.
exactly.
Okay, that makes sense. But what creates these magnetic fields in the first place?
So this is where it gets really interesting. Moving electric charges.
Oh, wow.
That is the source of magnetic fields. And actually, electricity and magnetism are so intertwined
Yeah.
that they're considered two sides of the same fundamental force,
Really?
which is electromagnetism.
So they're not just related.
Yeah.
They're actually two aspects of the same phenomenon.
That's exactly right.
That's crazy. How do moving electric charges create that magnetic force?
Well, think of it this way. Every time an electric charge moves, it generates a magnetic field around it. It's like an invisible whirlpool
Oh, okay.
that's swirling around that moving charge.
So each little charge has its own little whirlpool.
Yeah.
Yeah.
And when
Huh.
you have lots of charges moving together, like an electric current flowing through a wire,
Yeah.
all those tiny magnetic fields from those little whirlpools, they combine to make a bigger, more powerful magnetic field.
It's like a team effort.
Exactly.
All these little magnetic whirlpools
Mhm.
joining forces to create like this magnetic superpower.
You got it.
We've talked about magnets in general,
Yeah.
but I know not all materials actually respond to magnets in the same way.
That is very true.
Yeah.
You can actually classify materials into three main categories
Okay.
based on how they behave, magnetically speaking.
Okay.
So they're ferromagnetic,
Uh-huh.
paramagnetic,
Okay.
and diamagnetic.
So break down those magnetic personalities for me. I want to understand these different types of materials.
Yeah, so imagine a magnet as like a charismatic leader.
Okay.
Ferromagnetic materials, things like iron, nickel, cobalt,
Uh-huh.
they're like diehard fans.
Oh, okay.
They're strongly attracted to the magnet.
Gotcha.
So that's what's responsible for the classic image of a magnet picking up a jumble of paper clips.
Right, right. Those are the materials that are all in,
Yes,
magnetically speaking.
100%.
What about the other two?
So paramagnetic materials are like the casual followers.
Okay.
They're weakly attracted to the magnet.
Okay.
So they might be slightly influenced,
Mm-hmm.
but they're not going to, jump right in.
They're not going to go all the way.
Exactly.
Okay.
So aluminum and platinum, those fall into this category.
Okay. And then we have the complete opposites, the ones who want nothing to do with the magnet.
Exactly.
All
So
right.
diamagnetic materials,
Okay.
things like copper and gold,
Yeah.
they're completely indifferent to the magnet.
Mm-hmm.
They're not attracted at all.
Okay.
And sometimes they might even be slightly repelled.
It's like a magnetic popularity contest
Yeah.
with some materials
Yeah.
vying for the magnet's attention,
Mm-hmm.
and others couldn't care less.
Yeah. Perfect analogy.
So we've got these three different personalities, magnetically speaking.
Yes.
But let's delve a little deeper. Okay.
What's happening within these materials on a microscopic level?
Yeah. So we know that atoms have electrons
Right.
orbiting around a nucleus.
Yeah.
And those electrons, they're constantly in motion.
Those tiny little atomic whirlwinds?
Exactly.
Yeah, I remember those.
Each of those spinning electrons, they actually create a tiny magnetic field.
Wow. So each electron has its own little magnetic field.
A tiny one. And within a material, these atomic level magnets, they can group together into regions called magnetic domains.
So these are like tiny magnetic neighborhoods where the atomic magnets are all pointing in the same direction?
You got it. Now, in a non-magnetized material, these domains, they're kind of randomly oriented. And so their magnetic fields, they cancel each other out.
Okay.
But when you expose a ferromagnetic material, you know, like one of those diehard fans, to a strong external magnetic field, something really cool happens.
All the little atomic magnets, they suddenly snap into alignment.
Oh, wow.
So all the domains, they align themselves with the external magnetic field.
Okay.
And their individual magnetic fields all add up. So you end up with a much bigger, more powerful overall magnetic field.
So it's like a magnetic boot camp.
Yes.
Whipping all those disorganized domains into shape.
Exactly.
That's amazing. So that's how you magnetize something.
That's how you magnetize a material. And this helps explain, too, why magnets can lose their strength over time. You know, if you drop a magnet or you heat it up, you disrupt the alignment of those domains.
All right. Right.
So you weaken the overall magnetic field.
It's like you're shaking up those neatly arranged magnetic neighborhoods.
Exactly.
Okay, that makes sense.
Throw everything back into disarray.
So we've talked about these tiny magnetic domains. Let's go to the opposite end of the spectrum.
Okay.
Let's zoom out.
Yeah.
To the biggest magnet we know.
Okay.
Planet Earth.
That's a big one.
Remember how we were talking about moving electric charges create magnetic fields?
Yeah.
Well, it turns out our planet is a giant magnet.
That's right.
It's got its own magnetic field. And it's generated by the movement of molten iron in Earth's core.
It is.
Wait, so deep beneath our feet?
Yeah.
There's this churning sea of molten iron.
Yes.
Acting like this massive electromagnet.
It is.
Wow. And this planetary magnetic field, it extends far out into space, right?
It does.
Creating this kind of protective bubble around Earth.
Yes, it's called the magnetosphere.
Hold on. So we're not just talking about a cool scientific fact here.
Oh.
This magnetosphere is actually important.
It's incredibly important.
What does it actually do for us?
It plays a vital role in protecting life on Earth.
Oh, wow.
By deflecting harmful solar winds and cosmic rays.
What are those?
So those are streams of charged particles that are constantly bombarding our planet. From the sun and from outer space.
So our planet's magnetic field is kind of like a cosmic shield.
Exactly.
It's deflecting these invisible bullets that could potentially harm us.
That's right.
Wow.
Without it, our atmosphere would be stripped away.
Oh, no.
And life as we know it would be impossible.
So this isn't just some abstract concept. This magnetic field, this magnetosphere, it's essential for life on Earth.
100%.
Wow. Okay. So is this field static?
That is a great question.
Or is it always changing?
That's a great question. And it actually leads to one of the most mind-boggling aspects of Earth's magnetic field. It's not fixed.
What?
It can change. Over very long periods, it can change intensity. And even reverse direction entirely.
Really?
Yeah, these are called geomagnetic reversals.
Okay.
Where the magnetic north and south poles, they swap places.
Wow.
And it's recorded in the rock.
So the rocks themselves hold a history.
A hidden history of Earth's magnetic past.
Okay, so I'm picturing these ancient rocks, like a magnetic tape, preserving a record of these ancient flips.
Yeah.
How do scientists actually decode that? How do they read these magnetic messages?
Okay, so imagine a volcano.
Okay.
Erupting, spewing molten lava.
Yeah.
As that lava cools and solidifies into rock, there are these tiny magnetic minerals within it. And they align themselves with Earth's magnetic field at that time. So it's like taking a snapshot of the magnetic field. And preserving it within that rock.
So each layer of volcanic rock becomes this time capsule revealing the direction of Earth's magnetic field at that moment in time.
Exactly.
That's really cool.
So by studying these rock layers from different locations in different ages, scientists have actually pieced together like a timeline
Wow.
of Earth's magnetic field reversals.
And what have they found?
They found that these flips aren't actually rare occurrences.
Really?
They've happened hundreds of times
Oh.
throughout Earth's history.
So our planet's magnetic field is much more dynamic than I ever imagined.
It is.
But what actually causes these reversals? Is it like flipping a switch?
That's a question that scientists are still grappling with.
Okay.
It seems that reversals happen over hundreds to thousands of years.
So not instantaneous.
Not instantaneous.
Hmm.
During a reversal, the magnetic field weakens.
Okay.
Its structure gets more complex.
Uh-huh.
And you might even have multiple magnetic poles
Oh, wow.
emerging around the globe.
So imagine compasses going haywire,
Yeah, exactly.
pointing in all sorts of directions during these periods.
Yeah.
What impact would that have on life on Earth?
So that is a topic of a lot of research. It doesn't seem that reversals have caused mass extinctions
Okay.
or widespread catastrophes.
Okay.
But some studies do suggest that a weakened magnetic field during a reversal
Yeah.
might lead to increased radiation exposure on the surface.
Oh, okay.
So the effects on life are still being debated.
So it's a mystery still unfolding.
Yes,
Okay. You mentioned something before about animals using Earth's magnetic field to navigate.
I did. That's one of the coolest things.
Yeah, how do they do that?
It's like they have a built-in GPS.
I know. It's amazing.
So many animals, especially migratory birds,
Uh-huh.
sea turtles,
Yeah.
and even some insects
What?
have this incredible ability to sense Earth's magnetic field.
Wow.
And they use it as a navigational compass.
Okay, so how do they do that?
So scientists believe some animals have specialized cells
Okay.
containing tiny crystals of magnetite
Uh-huh.
as a naturally magnetic mineral.
Okay.
And these crystals act like microscopic compass needles,
Wow.
aligning themselves with Earth's magnetic field
Oh, okay.
and providing the animal with directional information.
So it's like they've got these miniature magnets inside their bodies,
Yeah,
guiding them on their journeys.
it is.
That's incredible.
Think about like migratory birds that fly thousands of miles every year,
Yeah.
crossing continents and oceans.
It's amazing.
They use a combination of cues,
Yeah.
the sun, the stars,
Okay.
and Earth's magnetic field
Wow.
to navigate with incredible precision.
It's like this intricate dance between biology and physics.
Yes.
Okay, so let's shift gears a little bit.
Okay.
From the natural world to the realm of technology. We talked about electromagnets before,
Yeah.
but what other ways do we harness this power of magnetism?
I mean, magnetism is at the heart of countless technologies
Yeah.
that we rely on every day.
Like what?
One of the biggest examples is data storage.
Oh, okay.
So hard drives in computers, magnetic tape,
Uh-huh.
they use magnetism to store information.
Oh, so all those digital photos and documents and videos and everything
Everything.
that we store on our
It's
computer.
all encoded using magnetism.
How does that work?
So think of a hard drive
Okay.
as a spinning disk
Yeah.
that's coated with a thin layer of magnetic material.
Uh-huh.
And you have tiny magnetic regions on this disk.
Okay.
And they can be magnetized in different directions.
Okay.
And that represents zeros and ones,
Oh, interesting.
the fundamental language of digital data.
It's like a magnetic Morse code
Yeah.
with these different magnetic orientations.
Exactly.
Representing the building blocks of our digital world.
Yeah, so as the disk spins,
Mm-hmm.
a read-write head, it hovers over the surface.
Okay.
It detects the magnetic orientation
Yeah.
of these regions to read the data,
Uh-huh.
or it can change their orientation
Okay.
to write new data.
So it's amazing to think that something invisible, this force, this magnetic force,
I know.
is holding all of our digital memories.
It is.
Okay, so data storage is one example.
Yeah.
What are some other ways we use magnetism in technology?
So many. I mean, magnetism is essential in electric motors,
Okay.
which convert electrical energy to mechanical energy.
Right, right.
So that powers everything from household appliances
Okay.
to
Yeah.
electric vehicles.
Yeah. I remember learning about those spinning electromagnets that make motors go.
Yes.
Okay.
And then you've got generators,
Uh-huh.
which do the opposite.
Okay.
They convert mechanical energy into electrical energy,
Okay.
and they rely on that interaction between magnetic fields and conductors
Yeah.
to generate electricity.
So whether it's powering our homes,
Yeah.
driving our cars,
Mhm.
storing our digital lives,
It's everywhere.
magnetism is kind of this silent but essential force
Yes.
shaping our technological world.
Yeah, and let's not forget one of the most futuristic applications,
Okay, what's that?
magnetic levitation trains.
Oh, yeah.
Maglev trains.
Those super fast trains that just kind of float above the tracks?
They do.
Tell me about those. How do those work?
So maglev trains use powerful electromagnets
Okay.
to levitate above the track.
So they're not actually touching.
No. They eliminate friction,
Okay.
and that allows them to reach incredible speeds.
Oh, wow.
You have magnets on the train and magnets on the track,
Okay.
and their interaction creates both lift and propulsion.
So they're literally riding on magnetism.
They are.
That's so cool. Every time we dive deeper into this topic, it's just more and more amazing applications.
I know.
So what about the future?
That's what I love to think about.
Yeah. What are some emerging technologies that might leverage the power of magnetism?
So many possibilities. Scientists are working on developing magnetic nanoparticles
Okay.
for targeted drug delivery.
What does that mean?
So imagine tiny magnetic particles that can carry medication directly to specific cells in the body,
Wow.
guided by external magnetic fields.
So instead of flooding the whole body with medication,
Yeah,
you can use magnetism to really target it.
pinpoint accuracy.
Wow, that's incredible. What else?
Another really exciting area is magnetic refrigeration.
Okay.
This is a technology that uses magnetic materials to create cooling effects.
Oh, wow.
So potentially leading to more efficient and environmentally friendly refrigerators and air conditioners.
So magnetism might be the key to a more sustainable future.
Possibly.
It's incredible to think about the potential from powering our homes and transportation
Yeah?
to maybe revolutionizing healthcare and fighting climate change.
Yeah.
Let's bring it back to Earth. Literally.
Okay.
We talked about how our planet has this incredible magnetic field
Yes.
generated by the movement of that molten iron in its core.
Yeah.
But we also learned that this field isn't static.
Right.
It can weaken, it can shift,
Uh-huh.
and even flip directions entirely.
It can.
What would happen if our magnetic shield were to weaken significantly or even disappear altogether?
That's a question that has sparked a lot of scientific curiosity. And, while we don't have all the answers yet,
Yeah.
we can kind of paint a picture of what a less than the magnetic future might look like.
Okay.
So remember how Earth's magnetic field acts like a shield, protecting us from those harmful solar winds and cosmic rays?
Yeah, it's like our planet's own personal force field, protecting us from those invisible cosmic bullets.
Exactly. If that shield were to weaken significantly or even disappear,
Yeah.
we'd be much more vulnerable to those charged particles from space.
Okay.
And that could have some pretty serious consequences.
I'm intrigued. Give me the rundown.
Okay, so one of the most immediate impacts would be on our technology.
Okay.
Solar storms, which are basically these bursts of energy from the sun, they can disrupt satellites, communication systems, even power grids.
Right.
And a weaker magnetic field would make us much more susceptible to those disruptions.
So imagine widespread blackouts, GPS systems going haywire, communication networks going down.
Yeah.
Sounds like a recipe for chaos.
It could be. And it's not just our technology at risk.
Oh, no. What else?
Well, there's also the potential impact on our atmosphere and climate.
A weakened magnetic field could mess with our weather, too.
It's a possibility that scientists are still studying. Yeah.
Oh, wow.
Some research suggests that changes in the magnetic field could influence atmospheric circulation patterns.
Okay.
And that could potentially affect weather patterns and climate over very long periods.
Okay, now I'm concerned.
Yeah.
Is there anything we can do about this? Can we somehow strengthen Earth's magnetic field?
That's the question, right?
Yeah.
Unfortunately, we don't really have the ability to directly control Earth's magnetic field.
Oh, okay.
It's a natural process driven by the dynamics of our planet's core.
So we're at the mercy of this invisible force that can just shift and change whenever it wants?
Kind of, yeah. We don't have direct control, but we're not completely powerless either.
Okay.
We can focus on developing technologies that are more resilient to solar storms
Oh, okay.
and improve our ability to predict and prepare for these space weather events.
So even though we can't control the magnetic field itself, we can take steps to protect ourselves
Exactly.
from its fluctuations.
Knowledge is power. The more we understand about Earth's magnetic field, the better equipped we'll be to adapt and to safeguard our planet and our tech.
It's like understanding the rules of the game.
Yeah.
Even if we can't control the players.
Exactly.
I like that analogy.
So as we wrap up our magnetic deep dive,
Yeah.
the key takeaway is that magnetism is so much more than just like a force of attraction or repulsion.
Right.
It's this fundamental force that shapes our planet,
Yeah.
guides animal migrations, powers our technologies, even protects us from harmful cosmic radiation.
It's amazing.
It is. And while we've uncovered a lot of really fascinating details about this invisible force today,
Yeah.
there's still so much more to explore.
Always more to learn.
Who knows what incredible discoveries and innovations await us as we continue to delve into the mysteries of magnetism.
Well, on that note, we've reached the end of our magnetic journey.
It's been fun.
We hope this deep dive has sparked your curiosity and left you with a new appreciation for these invisible forces that shape our world. So until next time, keep exploring, keep questioning.
Keep that magnetic curiosity alive.
Thanks for listening, everyone.